where we were last time was we were talking about resting membrane potential and then changing resting membrane potential, right? Depolarizing, hyperpolarizing, repolarizing, right? Okay, so let's start out there. If I show you this figure, a couple of questions for you. First, how does the cell get to minus 70? How does it get there, though? Not gated. Leak channels, right? And it's the unequal leaking of sodium and calcium, sodium and potassium through the leak channels, right? So that's how it gets to minus 70. And then let's just do it the simplest way possible. So if you are going to depolarize from resting and go towards zero, what is the most likely type of channel to be involved? What? Gated sodium channels, exactly, gated sodium channels. And then if you're going to be going from minus 70 away to, for instance, maybe minus 90, what is the most likely type of channel? Gated potassium channels. Okay, now repolarization is going from a depolarized state back to resting membrane potential, and what's the most likely type of channel to be involved in that? Be more specific. Gated potassium, exactly, gated potassium. And today we're going to be specific about what kinds of gates, so you need to know the difference between leaks, gated, and then today we're going to separate chemical gated and voltage gated. So we're going to have to be really specific about what we're talking about, what opens, what closes, and all that kind of stuff. So just starting out with that practice. Okay, so now we know the concept of depolarization and hyperpolarization. So what I'm going to do is I'm going to start at cell at resting membrane potential, which is minus 70 approximately. And then the first type of change in resting membrane potential that you can do is called a graded or local membrane potential. So it's going to be called graded or local. Let me show you what it looks like, and then I'll explain to you how it gets that way. So these are both graded potentials. They're minor changes in the cell membrane resting potential, and they could be caused, for instance, by opening or closing a gated ion channel. Does that make sense to you? So if you're measuring the resting membrane potential, right, and it's minus 70, and then you open a gated ion channel, then it will change by going down or going up, right? Okay, so you guys tell me, just given this figure, this one right here, the first one, Y, was probably a result of opening what kind of channel? Gated potassium. And this was probably a result of opening gated sodium. Does that make sense to you? Okay, so these are called graded potentials or local potentials. Let me explain to you first why they're called local potentials. And the local potential means that, let's look at a neuron, for instance. Where are you, neuron? Okay, so look with me here. So here's your typical neuron. You've got the cell body with the dendrites, right? And then you've got the axon. So what they're going to do is they're going to measure the voltage change at two different locations. They're going to measure it right here, and then they're going to measure it at the axon hillock. Okay? So this is called a local potential because if, for instance, let's say it's a chemical gated ion channel. Let's say it's a chemical gated sodium channel, for instance, right? The chemical binds and opens the chemical gated sodium channel, and sodium moves in, and it's going to cause a voltage change that is largest at the site, right? And as you move away from the site, it's less dramatic. You might not even feel it at all. So I always think of this as like dropping a pebble in a pond. If you drop a pebble in a pond, it creates waves, but you're not going to feel it on the other side of the pond, right? But what if I open 10,000 chemical gated sodium channels simultaneously? That's like dropping a freaking boulder in the pond, right? And you're likely to feel it all the way over there. So first thing is it's called local because you're more likely to feel the voltage change close to the site, okay? And then it's called graded because you can have strong ones and weak ones. So let's talk about the strong ones versus weak ones. Okay, so in this situation, graded, like different grades, it can be strong or weak. This situation might be X was opening 5 chemical gated sodium channels with 5 molecules of maybe acetylcholine, right? Okay, and this was 10 molecules of acetylcholine opening 10 channels. So do you see that it can be strong or weak, and then you feel it more at the site than you do further away. So that's why it's called graded, strong or weak, and local, because you feel it different. That makes sense? Okay, so Graded potentials may be depolarizing or hyperpolarizing, depending on what kind of gated channel you open. And these most commonly are associated with opening a gated ion channel. So very quickly, and this is easy, but we're going to use it as a starting point because when we do action potentials, it gets harder. All I want you to do here is on your paper, sketch the membrane potential recorded as the cell begins at resting membrane potential and then undergoes a hyperpolarizing graded potential. So you guys can do it, right? Yes? Where does it begin? Minus 70. Okay. Begin at rest. Hyperpolarizing graded potential.
You're going to go opposite.
Yeah, you're going to go down. So now I want you to label that and that. What kind of channel is involved there and what kind of channel is involved there. So let's call them A and B. What kind of channel is involved in A? What kind of channel is involved in getting you to minus 70?
League channels.
League channels. What kind of channel is involved generally in a hyperpolarizing graded potential? Be more specific. Gated potassium. And for right now, what I want us to do is to agree on calling these chemical gated. They don't have to be chemical gated, but we're going to contrast it with voltage gated later. Okay, so these are definitely going to be different than voltage gated. So call them chemical gated for now. And I'll explain. So chemical gated potassium. All right, and then the same thing on the next one. On this one, just sketch the membrane potential recorded in a cell as it begins at rest and undergoes a depolarizing graded potential. And then identify the channels that are involved. So that one's going to be pretty simple, right? You're going to start at minus 70, and you're going to go along, and then you're going to undergo a depolarizing graded potential, and it's going to look like that, right? And so you know how you got here. How do you get there? Gated sodium, and let's call it a chemical gated sodium because it's definitely not a voltage. We'll see what the voltage ones do in a second. Everybody okay with that? So keep that in mind because we're going to use that as a starting point for the next thing that we're going to do. So let's say the stimulus, acetylcholine, the chemical, binds and opens a chemical gated sodium channel in one area of the cell membrane, and that would cause what? Depolarization or hyperpolarization? We're just going to stick to the sodium example for a second. If you open a chemical gated sodium channel, it's going to cause depolarization. Okay, so the note is this doesn't have to be a chemical. For instance, your eyes have photon gated sodium channels, but I don't know how the hell to draw one of those or even imagine one in my puny little brain. You have pressure gated channels and temperature gated channels, but it's easiest to conceptualize chemical gated channels because you can picture the chemical binding to the ion channel and opening or closing it, okay? But what I'm telling you is it doesn't have to be a chemical. It's just the best way to start the story to get you to the voltage gated ones later that are going to be different. So you have light, stress, temperature, all of those kinds of gated channels. So let me show you an animation to give you the visual of the chemical gated channel. So this is... We're not going to watch the beginning of it because you don't know that part yet. All right, so one cell releases a chemical messenger. It's acetylcholine. In this instance, it's behaving as a neurotransmitter. Acetylcholine diffuses across the synaptic cleft and binds to and opens a ligand or chemical gated sodium channel. And then sodium rushes in, what polarizing the cell? Depolarizing the cell. Okay, and then the next part of the story is going to follow this potentially, okay? So you have rushing in and depolarizing the cell. So if in a neuron, for instance, and we're going to be talking about electrically excitable tissues, neurons and muscle cells for a while, if in a neuron the initial stimulus was abundant or really strong, like instead of 10 molecules of acetylcholine, you have 10,000 molecules of acetylcholine. If the initial stimulus was intense enough, then you'll open a whole bunch of those channels, right? A whole bunch of ligand-gated channels. And lots of sodium will move in, and it'll cause a big depolarization, right? So it's a boulder in the pond instead of a pebble in the pond. You guys with me? So this depolarization... So if the depolarization is really great, instead of going from minus 70 to minus 65, it might go from minus 70 to minus 55. Do you see? Okay? You can cause a big depolarization if you let a whole bunch of sodium in. Everybody good with that? So, as sodium floods in, remember that that causes a current change, right? Ions moving across a charged membrane is what we conceptualize as current with physiology. So you're going to cause a voltage change. And it can be big enough that it will actually impact an area that's not right next to it, right? Like across the pond. You guys with me? So what I'm saying is, if in this neuron you dump a whole bunch of acetylcholine on and it opens 10,000 channels, causes a massive voltage change such that this area also has a voltage change. It'll never be as strong, but it's going to hit over there pretty strong because you dropped a boulder in the pond. Okay, so what's going to happen is if you make a big enough voltage change to open a voltage-gated channel, you have hit what we call threshold. Threshold opens the first voltage-gated channel. And in our example that we're doing, most voltage-gated channels, voltage-gated sodium channels, are set at minus 55 millivolts. And minus 55 millivolts will be threshold. So, what is special about threshold? Threshold average is minus 55. It's not exactly there in all electrically excitable tissues. Threshold stimulus or stronger will result in an action potential, and an action potential is when you involve the next kind of channel. The next kind of channel is a voltage-gated channel, right? So do you see that we just caused a massive voltage change in the cell membrane? Yes? Okay. We went from minus 70 to minus 55, right? Maybe even all the way up to 0, right? So there is another kind of channel that is present only in electrically excitable tissues, and it's called a voltage-gated sodium channel, okay? This voltage-gated sodium channel. And so what I want you to imagine, to put the A together with the P for a second, is remember learning in anatomy, neuron, cell body or soma with a dendrite sticking off of it, right? And then attached is a single axon, right? And you have always learned this. You have always learned that the dendrites receive information and the axon sends it. But now you can put that together with the story that we're telling, because the dendrite receives information in the form of the chemicals, which open those chemical-gated channels. Yes? Okay? So they're actually sort of behaving as kind of receptors, right? Do you see that? Yeah? So the chemical binds and opens the chemical-gated channel, and so the cell is going to respond to it. And the way it's going to respond to it is at the axon hillock, you have your very first voltage-gated channels. So if you created a massive voltage change over there such that over here I hit minus 55, then you will open your first voltage-gated channel, right? So it has to be a boulder, not a pebble, right? You're not going to get a single molecule of acetylcholine over there that's going to cause a massive change over here, okay? So I'm going to open my first voltage-gated channel. But the voltage-gated channels are all lined up along the axon like little dominoes. So when this one opens, it is a voltage-gated sodium channel. When you open a voltage-gated sodium channel here, it lets sodium in, right? And then it will depolarize such that this one is probably going to open, because they all open at minus 55 or more depolarized, right? So if this one hit minus 55 and then allows more sodium in, can you see how it's almost guaranteeing that this one will hit minus 55, allow more sodium in? This one will hit minus 55 and more sodium in, all along the entire length of the axon until you hit the axon terminals, and then the cell's over, right? So as long as you line up your dominoes properly, you only have to flip the first one, right? Does that make sense? So this is a classic example of what? If sodium rushing in depolarizes the cell enough to open a sodium channel, which allows more sodium rushing in, which depolarizes enough to open another sodium channel, more sodium, what is it? Yeah, this is a classic example of positive feedback, isn't it? Okay. And remember, the positive feedback was what you did when you didn't want to fart around once you started something, right? Like, I started it, I'm going to finish it. How fast can you finish this? The fastest axons in your body go about 250 miles an hour. So once you get the first one open, you open every single one as long as somebody set up the dominoes properly. And if they didn't, that cell would probably be dead by now. Does that make sense to you guys? Okay. So it was called a graded or local potential when you were using, for instance, chemical-gated channels, but as soon as you open the first voltage-gated channel, then it's called an action potential, right? And action potentials are unique to neurons and muscle cells, your electrically excitable tissues. And who the hell cares, and why do you want to know this? Because The action potential will cause neurotransmitter release ultimately in a neuron cell. And the action potential will cause muscle contraction in a muscle cell, right? So this is the stimulus that allows for those things that are physiologically important. They depend on the action potential. Does that make sense to you guys? So let's go back, look at your notes, and then we will look at the diagram for it. Okay, so an action potential is a larger depolarization. Interestingly, all of the action potentials that we have run into are all depolarizing. In theory, you could have a hyperpolarizing action potential, but we don't. We've never found any. So all of the action potentials are depolarizing. Do you see what a massive depolarization it is? Once you open the first voltage-gated channel, then it causes all of them to open along the entire thing. So this is what an action potential looks like. And then we're going to put in the details of what channels are opening and closing at each point in the action potential in just a second. Okay, so it is a larger depolarization caused by the opening of voltage-gated channels, and it propagates itself. It's self-propagating. Hit the first domino, it'll take care of all the rest. And it doesn't lose magnitude. So when I say that the action potential is like constant or doesn't lose magnitude, I don't mean that it doesn't go up and down. I mean that whereas with graded potentials, if you felt it over here, it would be strong, and you felt it over here, it would be weak. That's not the case with action potentials. They run all along the entire cell, okay? All right, so what happens is your voltage-gated sodium channels open, and the axon hillock has the first concentration of them. So you set up a whole bunch of dominoes at the beginning just to make sure you really got it going, right? And then they're sort of lined up all along the axon after that. So many ions rush in as the voltage-gated sodium channels open and depolarization occurs, and then it moves down the entire axon as a wave of depolarization. And it's self-propagating. And the electrical change is huge in the cell. So when you hit your action potential, you're at minus 55, but you can completely flip the charge, go past 0 all the way to positive 30, because you let so many positives in, because you opened every single voltage-gated sodium channel that you had. Does that make sense to you guys? So it's a massive change because you open every single channel. Okay, so the electrical change is super duper dramatic, all the way from minus 70, sometimes up to positive 30. And so we did this to send a signal all the way to the end. But conceptually, does it make sense to you that I can't send another signal until I, for instance, fix how the polarized nature is and stick it back to minus 70 so that it can get to minus 55 again, and put sodium back in the right place so that sodium would move where I wanted it to? So I just did a big wave of depolarization, and now I'm going to have to do repolarization before I can ever use that cell again to send another action potential. So repolarization is getting the cell back to resting membrane potential, yes, and getting all the ions in the right place. I want to do it as quickly as possible. You will see in just a minute that there is a reason that neurons have to repolarize super quickly. So I want to do it as quickly as possible. So when I get up to here, this has all been opening voltage-gated sodium channels, right? Depolarization. What's going to happen when I hit the top of the hill and I want to go down? What do I have to do? Yeah, there's two things that have to happen. It doesn't really matter what order they happen in, but she was right. Open gated potassium channels. They are voltage-gated potassium channels, and they are set at a voltage that's way up here. So you can make sure you don't hit them before you hit the sodium, right? But what else do you have to do up there? You have to open your voltage-gated potassium channels. You have to close your voltage-gated sodium channels, yes? And it really doesn't matter which order you do it in. Either way, you're going to like crest the hill and start going back down, okay? Does that make sense? So you close your voltage-gated sodium channels, open your voltage-gated potassium channels, and then you're going to head down for repolarization. When you're heading down here, what is pretty much the only thing that's open? Yeah, it's potassium. It's your voltage-gated potassium channels. And since it's just diffusion, it's not an exact science, it usually slightly hyperpolarizes as it's doing the repolarization thing. Okay, so now what I've done is I let in massive amounts of sodium, stop that, let out massive amounts of potassium. Now the number is fixed pretty much, or close, but everything's in the wrong place. So how do you fix that? Sodium potassium pump. So we have been using the pump the entire time, but after you just jack up all your ions, you're going to have to use it a ton, okay? So the pump really doesn't change the number very much, but you can't say that you're done repolarizing until you put sodium back where it goes. Otherwise, if you tried to depolarize again, it wouldn't move, right? Does that make sense? So the ion channels really fix the number, but the pump will fix the concentration gradients. So the pump is going to be working really hard right here. It worked the entire time. It's just going to be working harder there. Okay, so repolarization. Now, repolarization in theory could, so I depolarize the cell body over here with chemical-gated sodium channels, right? If you make a big enough depolarization, you open the first voltage-gated sodium channel, and then it goes all the way down. In theory, I could depolarize the entire thing and then repolarize the entire thing. But that would mean that there was a lag time in which you really couldn't use the cell, right? While you were waiting for repolarization. So instead of doing it that one fell swoop and then the next thing, what happens is you actually chase depolarization with repolarization. So what happens is I'm going to open my first voltage-gated sodium channel. Sodium's going to rush in, which will cause this sodium channel to open, right? And then behind me, I am going to close sodium, open potassium, pump my little buns off, right? And then I'm going to open this one. Close sodium, open potassium, pump my little buns off. All the way to the end of the cell. So when I finish depolarizing, I am almost repolarized, right? Because that means I can use that cell very quickly again, right? And the nervous system depends on you being able to send action potentials frequently. Does that make sense to you guys? So you chase depolarization with repolarization, okay? All right, so show you guys an animation and then we will do the graph. Okay, so let's look at those voltage-gated ion channels. So this is not showing you the chemical-gated ones. This is just showing you a zap light that represents you hit minus 55. Okay, so they're just simplifying it by representing hitting minus 55. So zap, and then that one opens. What kind of channel is this? Voltage-gated sodium channel. So now I am in, pause. Which phase of this graph? Phase 1, exactly. I'm past here because here wasn't involved with voltage-gated channels, and now I'm here, okay? Voltage-gated sodium channels. Okay, keep going for a minute, still in phase 1. Now I open my potassium channels. Now, although I wish that they always did it the other way, because to me, it would be far more organized if you just closed your damn sodium before you opened your potassium, right? You got to put away your art supplies before you can play Minecraft at my house, but that is not how it works here. Okay, so here in some cells they open the potassium before they close the sodium. It doesn't really make any difference. But where are you? Right here? Where are you on this graph? Nope. You're at the top, right here at the top. The entire thing is the action potential, but you're at the top. You're at the crest of the hill. You're about to go down, right? All right, so now, see what happens. Yes, So now,
And what would be your cue that it's voltage?
I told you.
No, I don't remember what you said. Like, was it that it was?
These?
It goes above.
Okay, you are, when you're down here, before you have hit an action potential, it's all chemical gated channels, or at least not voltage. Yeah, minus 55 is threshold, and that's when you involve the voltage gated channels, yes.
And on the figure, when you're like seeing it going out, would there any way you would be able to tell that or not really?
No, except that they have these activation gates and inactivation gates, which is true of the voltage-gated sodium channels. So look here for a second. So we were right here, and that was at the crest of the hill, right? Mm-hmm. But the sodium channel actually has two gates. It's got one that opens, and it's got another one that closes at a different voltage. So now, watch. Now that sodium channel is closed, okay? So now where are we in the story? Now we're phase 2 because only potassium is moving. Does that make sense? And now we're heading down the repolarization, okay? So, and as long as the potassium is open, we're going to be repolarizing. And then watch, something important is going to happen. Then my sodium channel is going to be reset, but my potassium channel takes a minute. It stays open for a little while. So we're going to come back to that in just a second. Okay, so potassium is involved in the repolarization, right? But like I said, it slightly overshoots. You don't have to do anything special to get it back to resting membrane potential. Usually just the action of the pump and the diffusion will do it. So there isn't really even a name for that, except they call it the like after hyperpolarization or something. It just happens right after that. So at the end, they don't show it on this figure, but at the end, you have to use the pump even more, right? Because you've got all of your ions in the wrong place. But again, the pump doesn't dramatically change the electrical nature of the membrane, so they don't usually draw it in here, right? Because it's really the ion channels that change the electrical nature of the membrane. But the pump conceptually has to work or you'll never be able to use this cell again for that purpose. So this is called an action potential. Okay, so on this diagram, I'm going to have you guys do the action potential, and then you are going to tell me at each stage what kind of channel, and is it opening or closing, okay? Because there's close, there's open, there's different channels at each stage. Okay, so you already know this, and I don't want you to have to write it again, but I'm going to ask you, how did I get here? Leak channels, exactly. And so now I'm going to go from here to here, from minus 70 to minus 55. What kind of channels doing what? Nope. No voltage yet. Yeah, these are chemical gated what? Sodium channels, opening or closing? Opening. Got it? Okay. You don't have to worry about closing those because as soon as the acetylcholine falls off, they'll close on their own. And the acetylcholine just diffuses out of the synapse, or you can pull it out of the synapse with some stuff, and we'll worry about that when we talk about synapses. Okay, so now I get to minus 55, right? And so I'm going to go up. So what kind of channel doing what is here? Voltage. These are voltage gated. Sodium, opening or closing? Open. No, opening. Got it? Okay, now I'm going to crest the hill right here. And when you are cresting the hill, two things happen. It doesn't really matter what order, but what are the two things that happen? Go ahead. Voltage gated, potassium does what? Open. And?
Voltage gated, sodium closes.
Yeah, good. Good? Okay, and then you're going to head down. And although it already happened, I want you to tell me what's true here. What kind of channel is responsible for you heading down there? Yeah, it's the voltage-gated potassium, I'm just going to say, are still open, right? That makes sense? Okay. And then you're going to slightly sometimes hyperpolarize when you come down here, and that's also because of voltage-gated potassium. Does that make sense? Okay. And so when are you using the sodium potassium pump? Yes. The entire time, right? But when are you really, really working hard with your sodium potassium pumps? Yeah, this whole region right here, right? Okay, at the end and after you're going to be using it. Does that make sense to you guys? Are we okay with that? Okay. Yes? No? You're not going to talk to me? Go ahead.
So the only time that we're using a voltage-gated channel that is underneath the threshold is when it's at the very end, when it's going past with the.
Oh, at the end?
Yeah.
So this is all pre-action potential. You can use voltage-gated channels the entire rest of the time, okay? But then they're going to be reset, and you're not going to use them again unless you depolarize from resting membrane potential. Yes. So getting to my action potential, it's going to be chemical gated because you haven't made a big voltage change yet, right? You got to do something to let sodium in to cause a massive disturbance in the cell membrane so you can open the first voltage-gated one. And the important thing to understand about this is that we already said that all cell membranes have a similar resting potential, minus 70, right? Okay. And all cell membranes can have graded potentials, which is what's happening right here, right? But only neurons and muscle cells have voltage-gated channels, so they're the only ones that can have an action potential. Go ahead.
So the pumps go skate it back to
No, the pump doesn't really mess with the number very much.
but that's where it's trying, like, once it hyperpolarizes, you're trying to still get back to 70 now.
No, it's actually just trying to do the position of the ions. It does help a little bit with putting it where it got back where it is, but a lot of it just happens by diffusion. So the pump is not dramatic. It's never usually told in this story because it doesn't actually affect the number very much. But I want you guys to understand that although the number matters, yes, giving it back to -70, if I don't put my sodium back outside the cell, then I could never use this again, right? Because you can only tell the story once if you don't put the ions back where you got them, right? Because if you fixed the number and then didn't fix the position of the ions and then tried to use acetylcholine to depolarize from here to here, sodium wouldn't move in, right? If you still have tons of sodium in from the last action potential, then you're not going to be able to use it again. So you have to fix the number, but you also have to fix the location, or else it's just pointless. You could only use this once. Is that okay?
And you said
Okay.
neurons and muscles are the only ones that are
Yeah,
used in
neurons and
voltage?
muscles, right?
Neurons and muscle cells are the only cells with voltage-gated channels. And that's why, by the way, you've always been told that those are electrically excitable tissues, or neurons and muscles, nervous system and muscles are electrical systems. They're electrical because they have voltage-gated channels, right? That makes sense? Okay, let's look here. So this animation is a little longer than I want it to be, so be patient, but it's actually a good visual, and I know some of you guys are visual learners. I am not, so I'm doing this for you. It's going to put the whole story together.
Neurons send signals over long distances by generating and propagating action potentials. Most action potentials originate near the axon hillock of the cell body, in the initial segment of the axon. It then travels the entire length of the axon. A closer look reveals that during an action potential, voltage-gated channels open and close, altering the permeability of the plasma membrane to sodium and potassium ions. A threshold stimulus changes the shape of the voltage-gated sodium channels, causing their activation gates to open. This event marks the beginning of phase 1 of the action potential, known as depolarization. As sodium ions diffuse into the axon, the membrane potential becomes less negative. This causes more voltage-gated sodium channels to open, and the membrane potential soars to plus 30 millivolts. At this point, two key events occur. The inactivation gates of voltage-gated sodium channels close, and voltage-gated potassium channels open. These two events mark the beginning of phase 2 of the action potential, known as repolarization. As potassium ions diffuse out of the axon, the membrane potential becomes negative again. However, the membrane potential continues in the negative direction, going beyond the resting state of minus 70 millivolts. This marks the beginning of phase 3 of the action potential, known as hyperpolarization. During this phase, voltage-gated potassium channels close and all voltage-gated sodium channels are released from inactivation. By the end of this phase, ions move through leak channels only, and the membrane potential returns to the resting state of minus 70 millivolts. The neuron is now ready to fire another action potential. Summary: generation of an action potential. A threshold stimulus opens voltage-gated sodium channels. Sodium ions diffuse into the axon, depolarizing it to plus 30 millivolts. Voltage-gated sodium channels close, and voltage-gated potassium channels open. Potassium ions diffuse out of the axon, repolarizing it to a negative value. the membrane potential briefly hyperpolarizes. Voltage-gated potassium channels close, and the membrane returns to the resting state of minus 70 millivolts.
Good? Okay, just to give you a visual so that you can put the channels together with the graph. My son was like, I can't believe you're making them listen to her voice. She is so boring. I was like, can't you just show them the pictures? Yeah, but I already told them the story. Sometimes they need to hear it from somebody else. Okay, so here's the deal. You can't use the cell again, like I said, until it's reset. And there's a period of time that the cell is sort of still busy with the first action potential or is immediately after the action potential, in which you can't get another action potential. And this is called the refractory period. Do you know the concept of refractory period? Usually people learn it first in human sexuality.
Yes.
Yeah. Human sexuality, the refractory period is the period of time after a male has an orgasm that he cannot have another one no matter how amazingly hot she is. It doesn't even make any difference. And women don't have one, just so you know. High five, sisters. Okay, we have no refractory period. So in neurons, the refractory period is the period of time during and after one action potential that you can't have another one no matter what. And then there's two different kinds of refractory periods, really. One of them is no way, no how, and the other one is maybe if she's amazing. Okay, so this is absolute refractory period. And notice during the absolute refractory period, you're still kind of busy with the action potential you're in the middle of. What I mean about that is that if this action potential initially started because you dumped a whole bunch of acetylcholine over there, right? I don't care how much you dump. You're not going to get another action potential while you're still in this period, right? You can't. And primarily what is happening here is that the voltage-gated sodium channels are still busy from the last one. So conceptually, just put this together. Do you see that right here? No matter what you did over there, you couldn't get another action potential because you're still in the middle of the first one, right? Okay, and so that's the absolute refractory period. But so is that, because now even if I open them, no sodium would move, right? So my absolute refractory period is pretty much until I get my sodium channels reset to their original positions, right? Then potentially I could have an action potential. So the absolute refractory period right here, no way, no how, primarily has to do with the position of the voltage-gated sodium channels, right? Until they're back to their original position, you can't have another action potentials. But then notice right here, for instance, it's not going to be easy to get an action potential because my potassium channels are open, right? And they're going to be kind of working against me for depolarization. And or I could also slightly be hyperpolarized. And wouldn't it be harder to go from minus 80 to minus 55 than it was to go from minus 70 to minus 55? So the relative refractory period is you can get an action potential, maybe, but it's going to take you way more stimulus than it took you the first time. So if it took you 100 molecules of acetylcholine to hit threshold the first time, if you're here, it might take you 250, right? So that's called the relative refractory period. And the relative refractory period has to do with the fact that either you're slightly hyperpolarized or your potassium channels are still open. Does that make sense? Okay, so absolute and relative refractory period. Okay, so here's the deal, and here's something that's true about neurons and muscle cells that they only figured out, I don't know, relatively recently as far as physiology goes. I think it was about 25 years ago, but all or none property of action potentials. When you're talking about an action potential in a cell, there's no such thing as a strong action potential or a weak action potential. So here's an action potential in a given cell. Hold on, where are you, action potential? Lost it. Okay, here's an action potential in a given cell. If I started that with 100 molecules of acetylcholine or 10,000 molecules of acetylcholine, it doesn't make any difference. The action potential is going to be exactly a similar magnitude, right? Because when you open the first voltage-gated sodium channel, you open all of them. Okay, so there is no strong or weak action potential. The deal with action potentials is if you hit threshold, you get the entire thing, and if you don't, you don't. Right? So it's all or none. If you hit minus 55 or further depolarized, then you get an action potential. And it's the same, regardless if you hit minus 55 or went all the way to 0. It doesn't make any difference, right? So you open all of them. So that brings up a question. if all action potentials are the same, how does the nervous system code for intensity, for instance? Because there's no strong action potential or weak action potential. Okay, so how does the nervous system code for intensity? So assuming that I could control for the number of neurons I was dealing, what I want to know is what's the difference in the nervous system action potentials in poking my finger with a pin versus cutting my damn finger off? It is frequency. It's a frequency coding thing. So with the nervous system, intensity is coded by frequency. So if I poke my finger with a pin, imagine it going action potential, pain, pain. And if I cut my damn finger off, then it goes pain, 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 pain as fast as it possibly can. Does that make sense? If I have photon-gated channels in my eyeballs and there's more light, it sends more frequent action potentials down my optic nerve. Does that make sense? Same way on the way out, although sensory is an easier way to think about it. How do I, for instance, cause a stronger muscle contraction? I send more frequent action potentials to it. So the entire nervous system is very consistent about frequency coding. Now with that in mind, can you see why it's very, very important to repolarize quickly? Because you can't use frequency coding if you don't repolarize very quickly. Does that make sense? Okay, so the nervous system repolarizes the fastest, and then skeletal muscle, and then cardiac muscle, and then smooth muscle, really. Okay, so this is a visualization of the same thing. So what I want to tell you is, so intensity. So this is a subthreshold stimulus, and this is, by the way, just super oversimplifying what an action potential looks like. When they're drawing a lot of them, they usually just represent them as a spike. Does that make sense to you? So if you get a subthreshold stimulus, like this is kind of weak, right? So it was a little bit of light or a little teeny bit of pain. Then it's like, oh, I'm not even going to send one. Okay, but then this is like, oh, I'm feeling something, and I send one, right? So this is like a stronger impulse. This is even stronger, and you get more frequent action potentials. And this is cutting your damn finger off. That's what that is, right? Sending more and more and more and more frequent. How does this correspond to what we were talking about the chemical gated channels? Well, if down there at that end, I dump 100 molecules of acetylcholine, I might get this. If I dump 10,000, after I use the first one, I've still got more acetylcholine, so I send another action potential, right? And then I've still got more acetylcholine, right? So more chemical would send more frequent action potentials. Does that make sense? It's still frequency coding for intensity, isn't it? Yeah. Is that okay? So frequency coding is super duper consistent across the entire nervous system. It is how we talk about intensity. Okay. So this is called frequency coding. So here is a difference that's important between a graded potential and an action potential. A graded potential can be strong or weak. This is graded, yeah? And a graded potential can be hyperpolarizing or depolarizing. But an action potential is not strong or weak, and it's always what? It's always depolarizing, isn't it? They're always depolarizing. Is that okay? Okay, so you got to know the meanings of the terms. Graded and action mean very different things. Are we okay with that? Okay, go ahead.
So is it just not complete when it sends a whole bunch of, like the frequency, is the action potential just not complete?
No, you have to repolarize every single time. So what you are seeing is, for here, instance, this is 2, right? Action
So
potentials,
do they
yes?
just have relative refractory period? Like how?
No, it has to repolarize all the way. Or if it repolarizes just a relative refractory period, then it's going to be kind of sluggish. You're not going to be able to very easily get it back to an action potential. So in order to get frequent action potentials, you have to depolarize, you have to repolarize, right? And you have to do it quickly and dependably, or else you're not going to be able to use frequency coding. So this is not a continuous action potential. It's an action potential, go right back to resting, start it over again with the stimulus, action potential, right back to resting, start it over again with the stimulus. So you can, there is a refractory period. Yeah. Yeah, it's super fast. So you have to have this is why you really depend on those concentration gradients for sodium and potassium, right? You worked like the entire cell's life so that sodium will move quickly when you want it to, and potassium will move quickly when you want it to, right? And your sodium potassium pumps better hustle, or else you're going to have a useless nervous system, right? That makes sense? So all of this stuff has to happen really, really quickly. So the depolarization, I can't remember, I've got it written down somewhere. The depolarization in your nervous system the repolarization in your nervous system is the very fastest because we need these to be super duper sensitive. And there is a lag time, it's called synaptic delay, in which you can't quite get there. But fascinatingly, you can't notice the delay because your noticers have the delay. Like there's no way you could ever notice that there was a lag time with your neurons because your neurons are using that lag time to assess other neurons. So you could never even notice that there was one. So it has to be super duper fast, and especially in the nervous system. The second fastest is skeletal muscle. It has to repolarize really quickly too. So this is like nanoseconds that we're talking about here, okay? All right, so the entire story that we've been telling is for unmyelinated axons. And in a second, we're going to talk about myelinated axons. But before we do that, I want us to put the A together with the P. Okay, so what I want us to do is to look at this figure, and I want us to imagine that the story that we've been telling is happening on this cell. Okay, and so I'm going to ask you where on this cell body, axons, dendrites, axon, hillock, axon, you are going to find leak channels. Where do you think you're going to find the leak channels? The entire cell, because the entire cell has the resting membrane potential, right? Okay. How about sodium potassium pumps? Where are you going to find those? Everywhere, but you're going to need a whole bunch of them here, aren't you? Because they have to repolarize right behind the depolarization. So you're going to need them lined up along the entire axon, right? Because remember what you did is depolarize, close, repolarize, right? Pump. Okay. Now, where do you think you're going to find chemical gated sodium channels? Chemical gated. I can't hear you. Dendrites and cell body. Yes, that's what this is about. Remember? Dendrites and cell body are about receiving, right? They are going to receive the chemical that opens the chemical gated channels. Yes? So chemical gated sodium channels. Where do you think you're going to find voltage gated sodium channels? Axon hillock is where you're going to find the first ones, right? And then also along the entire length of the axon. Yes? And conceptually, where are you going to find voltage-gated potassium channels? Yes, they have to be all along the entire thing as well. Does that make sense? So if you start putting it in, you can start to see what has to happen in order for the other thing to happen, right? Okay, so this is consistent with the story that everybody's told you about neurons, right? You receive and then you send, you receive and then you send. And so you can look at a single neuron and always tell the direction that the information is flowing, right? Because you receive at the dendrites and then you send it out at the axons. And it really just has to do with how your dominoes are set up. However the dominoes are set up is how the thing's going to work, right? You flick the first one and then they're going to go all that direction. Good?
Voltage gated potassium
yes.
all over?
All over the axon. Just the axon. Yeah, all over the axon. Is that okay? All right. Okay, so we just did unmyelinated axons. And the way that I think of unmyelinated axons is the entire axon is kind of a whole bunch of little bitty dominoes, right? And if you hit the first one, you get the entire thing that falls. Does that make sense? But of course, you guys know that some axons are myelinated. As a matter of fact, a lot of axons are myelinated. So remind you what myelination looks like. So this is a myelinated axon. The longer an axon is, the more likely it is to be myelinated. And you've learned before that myelin is about insulating and speeding up the transmission. So now I'm going to explain to you how it works. Okay, so this is a myelinated axon. What happens at myelinated axons is you have this area that's myelinated and then an area that's not, and then you repeat that. Okay, this area that's not myelinated is called a node. Either a node of Ranvier or a neurofibril node, because nobody can decide what the hell they want to call them. If it says node, that's what they're talking about, right? It's the only one you've got. And what I want you to understand is that under the myelin, you let almost no ions in and out, but then at the nodes, you have a whole bunch of voltage-gated channels. So what's going to happen here is you are going to depolarize at the axon hillock massively. And then you're not going to let anything move as it goes under the myelin. And then it's going to be a big enough wave under the myelin that it will depolarize the next node. And then that node depolarizes and you make a big enough wave under the myelin that it depolarizes the next one, right? So the way to think about this one conceptually maybe is instead of a whole bunch of little bitty dominoes, just a few big ones, right? And if I knock this one over, it can knock the next one over. They have always called this saltatory conduction because it kind of appears to be jumping, and saltar means to jump. If you speak Spanish, saltar means to jump. So they call it saltatory conduction because it looks like it's jumping from node to node, but I actually think it's more diving, right? Because what you do is you make a big change and then you don't let it dissipate, right? And then it hits the next one, and then you make another big change and then you don't let it dissipate, right? So the myelin really doesn't allow for ions to move in and out, right? So can you see how it's insulating? Now, fascinatingly, this is way faster than an unmyelinated axon. Apparently, a few big dominoes are faster than a whole bunch of little ones. But this can also bring in, have you guys ever heard of disorders that demyelinate axons? Demyelinate, have you ever heard of those? MS is one of them. It causes a demyelination of axons, but I want you to think about that. If you demyelinate these axons, will they just work like the unmyelinated one did? No, because they only have the voltage-gated channels intermittently, right? So
pretty slow then?
they don't work at all.
Oh, at all.
You start, they say that with, what happens is you just try to send the transmission and the dominoes are not knocking each other over. So as soon as you start demyelinating, you're going to lose it. You could get it halfway down, but then you go into the demyelinated area and it won't go further. So you start losing control of your muscular activity, for instance, in the periphery. That makes sense? So it doesn't just go back to, oh, we'll just go slightly slower. It's like, no, now the anatomy is set up wrong and I can't actually get it.
Someone who becomes paralyzed because of MS.
Yeah, you can have paralysis because of MS, and it'll cause permanent changes in your neurons. Is that okay? That makes sense? So this is myelinated versus unmyelinated. And with myelinated, it's called saltatory conduction, and it tends to be faster. And when you have very long axons, like the longest axon in my body, which is way more impressive than somebody that's taller than me, goes from the lumbar region of my spinal cord all the way down to, for instance, my little toe. That's a single axon that goes all the way down there. So you can understand as you get them longer, then speed becomes pretty damn important, right? That makes sense? Okay, so that's saltatory conduction. There's a really good review of action potentials in interactive physiology. Have any of you guys used interactive physiology yet? It's really helpful when things start getting hairy, like they do with the nervous system. So I'm just going to remind you again that it can be very helpful. Okay? All right. So, questions? Anyone? Go ahead.
So we were going over chemical gated channels, like way back, and I was listening, but I missed. You said in the beginning. I know that we have the chemical gated sodium channel, so that's where the dendrites. That's where it's going to be.
Dendrites and cell body.
And cell body.
Yeah. I mean, you can think about it as dendrites later, and you will figure out that that's a guideline and not a rule. There can be other places. But first of all, it's easier to understand, like, conceptually where they usually are, and then there's a whole bunch of different shapes of neurons. I don't know if you remember learning about unipolar and bipolar and multipolar neurons. So I'm telling the story with a multipolar neuron. And then later on, we will figure out that there are other shapes, so there has to be different morphology for starting an action potential. So, does that make sense? Okay, so I won't test you over the exceptions. Later on, we'll conceptualize those. Other questions? Okay, so I'm going to tell you that this is the only stuff that's real physiology that we've done so far. So the rest of it was just trying to get you guys here. So I want you to understand that this is when I'm going to start testing you really hard. So you need to ask questions when you get confused, right? Because that's what I'm here for. So I want you to study this over the weekend. But first, we're going to sort of assess whether you get the normal physiology by breaking it. So we're going to do a little bit of pathophysiology, not so much because I'm trying to make you memorize pathological conditions, but because if I break it and then you can figure out what's going to happen, then you really understand how the normal physiology is going to work, right? That makes sense? So I'm going to throw a few pathophysiological situations at you. Okay, so you guys ready? And ask questions if you get confused here, because for some reason these, when you get home, trying to read them like completely throws people off. So make sure that you get it before you leave. Okay, here's what's going to happen. Sometimes you have fluctuations in concentrations of ions. And if you did, would it be more likely to occur in the ECF or the ICF? Yeah, ECF is the first to get disturbed before the ICF does, generally, okay? So what we are going to have is 4 different situations, and where the letter reads, right, hypokalemia, that is going to be the disturbance, and then what's after is everything that happens because of that disturbance, right? Okay, so hypokalemia is low, hypo, low what? Potassium, where? ECF. Low potassium in the ECF. Okay, and then we'll see what happens if you have low potassium in the ECF. Okay, so if I have low potassium in the extracellular fluid, it means that I am going to have a steeper concentration gradient for potassium than normal at rest, right? Because normally it's 30 to 1, right, inside to outside, and now it's 30 to 0.1, which is 300 to 1, right? Got a really steep concentration gradient. So let it sit there for a second with hypokalemia, and then more potassium than normal is going to leave the cell at rest, right? Because of the concentration gradient. And then sitting there at rest, the cell is going to become what? Slightly depolarized or hyperpolarized? If more potassium leaves, yeah? No? Hyper, yes. Potassium. Potassium, hyperpolarized. You with me? Okay. So now the cell is, instead of sitting at rest at -70, it's sitting at -78, okay, or -80, okay? Now, who cares? Well, electrically excitable tissues care, because now if the cell is hyperpolarized and I try to get to an action potential, I won't necessarily get there with the same level of stimulus, right? So it's going to be harder to hit threshold if you are hyperpolarized. So which body systems would this affect really dramatically? Any of your electrical systems, your nervous system, muscular, and cardiac muscle is a big deal because cardiac muscle depends on rhythmic depolarization and contraction. And if you can't do it when you meant to, you're going to lose your rhythmicity, aren't you? Right? If you depend on depolarization of atria, contraction, depolarization of ventricles, contraction, and instead you tried to depolarize my atria, screw it, I didn't make it, and then my ventricles contract when my atria hadn't contracted yet. Can you see how those cardiac arrhythmias can be big time problematic? So it makes it harder to depolarize, harder to send an action potential, and this causes muscle weakness, right? So your muscle cells do not contract every time you tell them to. And remember, it's frequency coding that gives you strength, right? So you don't get it every time you mean to. Fatigue, both mental and physical, right? Mental because of neuron activity and physical because of muscle. Sluggish reflexes for the same 2 reasons, right? And then the big one is cardiac arrhythmias. Cardiac arrhythmias can increase your likelihood of having a heart attack. They don't necessarily cause it, but yeah, they can increase your likelihood. So how would you get hypokalemia? Well, one of the problems with massive amounts of water loss is it's not just water that goes. So if you have vomiting, diarrhea, diuretics, you are losing tons of water-soluble ions at the same time you're losing the fluid. And those become more immediately problematic than even the fluid loss. So you can have vomiting, diarrhea, diuretics, also decreased intake, but it would have to be like massively decreased, like starvation conditions, to cause these kinds of problems. There are also hormones. One of them, we haven't learned its function yet. I'm going to put it in here later, so we can talk about it later. Aldosterone is one of the hormones that's involved in controlling sodium and potassium levels in your blood plasma. And then kidney failure can also do it. So one thing before we move on, vomiting, diarrhea, and diuretics are really, really big public health problems. I don't know if you know this, but diarrhea still worldwide is the leading killer of children worldwide. And the problem is not so much the fluid loss, it's the ion loss. And you can see when we get through, because there's going to be 3 different hypo situations. And a child who was dealing with massive amounts of diarrhea, like from cholera, for instance, would be dealing with potentially all 3 of them simultaneously. So, and diuretics are a big deal because, of course, some people use over-the-counter diuretics in a way that they're not meant to be used. It's not at all uncommon for people struggling with bulimia or anorexia to use diuretics to get rid of excess water weight. But do not think that just because they came over the counter, they can't kill you, because they can, because you can have massive losses of ions in this process. Okay, so now does hypokalemia make sense? Okay, you start with the disturbance and then you sort of read it stepwise. Hyperkalemia is really interesting too. Hyperkalemia is what level of what where? High potassium in the ECF. Okay, so that means that the concentration gradient for potassium at rest is going to be less steep than it should be, right? It should be 30 to 1, yes, but now it's 30 to 10 or 3 to 1, right? Makes sense? And yeah, that's going to cause an electrical change in the cell, but the big deal is that at that concentration gradient, when you depolarize and then try to repolarize, will you repolarize quickly if your concentration is 3 to 1 instead of 30 to 1? No, your repolarization is going to be limited by that concentration gradient. So too much potassium in the ECF makes it difficult to quickly repolarize. And if you can't repolarize, you get stuck in your refractory period. Either absolute or relative, right? One of them, you get stuck in that one of them. And again, that's a big deal with the heart, because if I depolarize and I can't repolarize, I can't use that cardiac muscle cell again, right? I cannot make it contract again if I can't repolarize it. So symptoms, massive disturbances in your EKG, severe muscle weakness. The muscle weakness can get severe enough that it can lead to paralysis. Usually it's temporary. And the big deal about this one, and the reason you may have heard about it before, is that this is how we kill people on purpose. This is the drug that actually does the lethal part of death by lethal injection. And I am from Texas, and if anybody knows about lethal injection, it's Texans, because if you kill us, we will kill you back, right? And for better or worse, Texas has more death penalty inmates than the entire rest of the country combined. And we make sure that they eventually die. So this was really, really mastered. And so what happens is generally that there's a 3-chemical cocktail, and this has become really controversial for a couple reasons I'll talk about in just a second. And it varies from state to state, but usually the first one is a muscle relaxer that they give you. And then the second one is a pain reliever and anti-anxiety medication. They don't want you to be stressed out. And then the third one is a super duper high concentration, like 60% concentration of potassium. And usually it's potassium chloride they inject you with. What happens is it massively floods your bloodstream, including your heart, and then your heart depolarizes, but it can't repolarize. And so what usually happens is it stops your heart within a matter of seconds to minutes. But we've been having a lot of trouble in this country with it lately. I don't know if you guys heard, like there's a big tragedy in Oklahoma in which they tried to use death by lethal injection, and the guy like lasted for like 72 hours. And so there's a couple of things that are going on. First of all, it has to be supervised by a physician. And a lot of physicians are saying, I'm not going to do that because I took the Hippocratic Oath that says first do no harm. So I'm not going to supervise death penalty situations. And then second, a lot of countries worldwide are doing away with the death penalties, and some of those countries are where we got our chemicals, and now they won't give them to us anymore. So the formulations for lethal injection are like really controversial right now, but all of them use high levels of potassium. So causes, by the way, up to 67% mortality if left untreated, but if you get it in higher concentration, then you can get the mortality rate up to almost 100% mortality. So causes, increased intake, but only if it was coupled with kidney insufficiency, because if you're taking in a bunch of potassium and your kidneys are working well, you just pee it out, right? Because it's water soluble. Death by lethal injection, and then fascinatingly, burn victims are at really, really high risk of hyperkalemia, because if you see, so imagine someone has like 3rd-degree burns over 80% of their body. Then you have potentially trillions of cells that were damaged, right? And when you damage the cell membrane, the potassium goes from the intracellular fluid to the extracellular fluid, correct? And then it circulates. And then it can hit your heart and cause cardiac arrest. Does that make sense? So burn victims are, among many other things, at very high risk for heart attack. So, and there's also hormone imbalance that can cause it. The same hormone, just in a different direction, different balance. Okay, so now let's talk about calcium. We haven't talked about calcium before, but it's part of the story. It's just sort of peripherally related. Okay, hypocalcemia The name implies what levels of what where? Low calcium extracellular fluid. Okay, so what does calcium have to do with the story? Well, nothing directly, but our gated sodium channels have a latch, so they don't just flop open. And the latch is extracellular calcium that's sitting out there, keeping them closed until you stimulate them. Okay, so now I lose extracellular calcium. And then some of the gated channels are a door without a latch, and they open when you didn't mean them to. Okay, does that make sense? So let that sit around for a little while. And if some, but not all of your sodium channels open when you didn't mean them to, that means that the cell at rest may be slightly what polarized? Slightly depolarized at rest. Okay, so now what I meant to be a graded potential becomes an action potential. And I get accidental action potentials. I send signals when I didn't mean to, because instead of sitting at minus 70, I'm sitting at minus 60, right? So things that were meant to be graded potentials become action potentials. And what happens is nerves and muscles have spontaneous, inappropriate action potentials, which can cause cramps and spasms, exaggerated reflexes, convulsions, tetanic muscle contraction, in which your muscles just will not relax at all. And it can get really serious. Most of us have experienced some kind of ion disturbance, maybe this one. The muscles around your eyes are really, really sensitive. And if you ever have those little twitches that go on in your eye that nobody can see but you, it's usually because of an ion disturbance. And one of the ions it can be is calcium. And so if you get slightly hypokalemic, then you get action potentials when you didn't mean to. It's also really likely to be a potassium disturbance, because that can cause it as well. So that is probably the situation in which you've run into it. So what are some causes? Decreased intake of calcium, but even more importantly, decreased amount of vitamin D. Because if you don't have vitamin D, it doesn't matter how much calcium you eat, right? Okay, so vitamin D deficiencies can cause calcium deficiencies. And then these are the two hormones, parathyroid hormone and calcitonin, which are specifically responsible for regulating calcium in the bloodstream. And if either of those is out of whack, you can have calcium problems. So symptoms of long-term low calcium that could lead to these hypocalcemia symptoms. Dry skin, psoriasis, coarse hair, brittle nails, which unfortunately are also symptoms of living in Utah. So I don't think that we're all hypocalcemic. We're just all in the desert. Okay, last one. This one's the most common. More people end up in the hospital with hyponatremia than the others. But not surprisingly, some of the hypos end up clustering together, because if you really are super dehydrated, in all likelihood you lost a lot of ions when you lost all that water, right? So hyponatremia is what level of what where? Low sodium extracellular fluid. Okay, so that means that the concentration gradient for sodium is not as steep as it should be. So it should be 15 to 1, right? Now let's say it's 5 to 1. Okay, that means that when I try to depolarize to get an action potential, I'm going to have trouble, right? So I'm going to be pretty sluggish, because it's not going to move very quickly at 5 to 1, right? Okay, so it causes muscle weakness and it causes nausea. But even more importantly, or more quickly important, I should say, it disturbs the osmosis of the cells. And so if you take a whole bunch of the sodium out of the extracellular fluid might go from being what tonic to what tonic? It was iso, and you lose a whole bunch of your extracellular sodium. Hypo, it goes to hypo. And what will happen to cells if they sit in a hypotonic solution for a while? They start to swell. Usually we don't get to the point that they pop, but the problem is that the brain gets really pissed off if you make its cells swell. A, there's no room for it to swell. And B, the structure of neurons will determine the function of neurons. And so what tends to happen is when people become hyponatremic, they start to act like nut jobs. They just act crazy, and a lot of times people think that they are on drugs. So you'll come into the emergency room and you'll just be acting like talking nonsense. And in addition, sometimes they get a little violent, but it's usually associated with such low blood pressure because you've had serious water loss that you're like trying to punch somebody, but you're gonna like fall over when you do it. So it's not like you're generally that dangerous. So you're acting crazy because your neurons are swelling, super low blood volume. And usually when they replace your ions and your fluids, you will start acting totally normal again. So why is this one the most common? Well, decreased intake, but not usually a problem here. But sweating, vomiting, diarrhea, and diuretics. In the middle of the summer is when this generally happens. When people are doing activities that makes them really, really sweat a lot, especially if you combine that with alcohol. So in Texas, you go out on the boat and you drink some beer all damn day long and you sweat your butt off, right? And then you continue. Lather, rinse, repeat over and over again, and then people end up in the hospital. It's even worse here in Utah if you do drink because the beer sucks. It's a diuretic with too much fluid in it, right? And so you got the diuretic effect. And so Utah beer really just makes you fat and disappointed and potentially hyponatremic. So sweating, vomiting, diarrhea, and diuretics. Kidney failure could also do it. Hormone imbalances, poor diet combined with lots of beer. And beer is worse than other alcohols because there's more water in it. So shots of tequila are far more effective, right? And then the last thing is, so we will talk about MDMA, which is ecstasy, and we'll talk about a bunch of the neuroactive drugs later. But I'm talking about ecstasy, for instance, for club use or illegal use right now, because there are actually therapeutic uses for ecstasy now. But club use, why have the few people who have died of ecstasy use died of it? It's not really to do specifically with like damage to neurons or damage to brain activity. It's to do with hyponatremia. Because
they're drinking more water?
No, they don't drink enough water. It actually depresses your thirst response. In addition to making you dance for 8 hours in the heat at Burning Man, it depresses your thirst response. And so you're not thirsty, you're becoming severely dehydrated and also losing your ions. And people die associated with it. And it's only been like 5 or 10 deaths associated with ecstasy use, but they have been associated with these ion imbalances. So that's MDMA. So this is the most common electrolyte imbalance. What was your question?
Is this common in pregnancy? Because my whole first trimester I was hospitalized for it.
Yeah, well, damn near everything that can go wrong will go wrong with pregnancy, because one of the things that happens is your little internal parasite hijacks your endocrine system and messes with the hormones. And primarily what they do is mess with the hormones so it suits them better. And sometimes it is at your expense. A lot of times it's at your expense. So for instance, if you're not feeding them enough calcium, they will start releasing chemicals which will break down your damn bone mass and feed them the calcium. So they're like the most effective parasite that has ever evolved, right? I mean, I love my little parasite, but you know. That's the end of that set of materials. So this and the last set of notes will be what your quiz is over on Tuesday. We will start new material on Tuesday, but it won't be on the first test. It'll be on the second test, okay? Oh, sorry, Monday. That whole part was supposed to say Monday. And then your test is a week from today, next Wednesday. Yeah? Okay.
Are you going to your office right now?